Hello and welcome to the physics lab. Today we're going to talk about the oscilloscope lab. And some of you found it disturbing during the last video because, or not the last video, one of the videos, because I said that I wasn't wearing any pants and I was joking around, and you realized that I wasn't wearing pants because I was wearing shorts. Well, this time I'm not wearing shorts. See, I'm wearing pants this time. Just thought you should know before we started the video. Anyway, for the oscilloscope lab, what do we use an oscilloscope for? Well, there's two things that it measures. See what it does? Well, it measures a signal like this. It's a nice sine wave. Remember, I didn't major in art here, so my sine waves aren't all that great. But there's two things that you have about a sine wave. One is the amplitude. That's from the peak to the valley. Or sometimes we call it peak to peak. It really isn't peak to peak, but that's the amplitude. And that's a voltage in our case. Most times it is a voltage. And then you have the period, which is the time from here to here, or the time from the peak to the next peak. Same thing. Depends, or even the valley to the valley. No, I'm not going to do my Valley Girl impression. So how do we measure all of this information? Well, that's what you use the oscilloscope for. Now, interestingly enough, and this you might have remembered from your other physics classes, this time right here, which is called the period and is denoted by T, if we take 1 over that, that's equal to the frequency. And most of the time, we're going to be dealing with frequency because that, as it turns out, is more interesting than the period. Okay, so we're all set, right? I knew you were. Oh, that's right. You're watching this on video, so you can't tell me. Anyway, so let's start off and talk a little bit about oscilloscopes. If we come over here, we see an oscilloscope. Yeah. This is what we used up until recently in this class. It was actually manufactured when I was in grade school. I think Abraham Lincoln's brother worked on it. That's how old it is. It's pathetic. You couldn't even use the handles because they would break off and drop the whole thing on the floor and make it smash to a million pieces. Not only that, is we also had to use a signal generator to make the signals that the oscilloscope would see. And then you'd have to run them back and forth with all these cables like this one here. We don't have to do that nowadays. Now, we can do all of this in something that fits inside this box. Yes, just this box. I could tell you a lot about boxes. In fact, I could give you a boxing lesson if you'd like. I don't think that would be appropriate. If we look inside the box, you'll see an empty box because the oscilloscope is actually over here. It fits nicely inside the box. And when you're done with the lab, that's where it should go. As you can see, each oscilloscope has a number. This number is 5. If you look at it upside down, it looks sort of like an S, but we're not going to do that. We're going to look at it like this, so it's a 5. When you come to get an oscilloscope from me, I will note which one you are using. It should be the same as your station number. So if you are at station 4, you should have oscilloscope number 4. And you should bring it back to me at the end of the lab. We have to keep track of these things. Alright? So we'll put it back in the box because we're not going to use this one here. This connects to the computer through a USB cable. So now we're going to go over to the lab and the station I set up, and we're going to measure we're going to start by measuring the amplitude. Amplitude is vertical. Time is horizontal. This is me clapping. Alright? And we're going to take a battery and we're going to measure it. So you need to get one of these batteries from the front. What the hell? Man, look at this battery. You don't want a battery like this. This battery has obviously been the victim of a crime because as you can see, someone scattered salt all over it. So it's a salt and battery. No, actually, that's just a really corroded battery. You want one that looks more like this. See? Yes, I planned that. So let's go over to the station here and see how we have it all set up. Remember, this oscilloscope actually not only takes the place of the big oscilloscope over there, it also takes the place of the signal generator. So even though we call it an O-scope or a scope, it's actually both the scope and the signal generator. That's not going to become important right away, but you'll want to remember it for later on. So then we'll move the mouse so that my screen comes back alive. Oh, that's wonderful. And this is what your Excel spreadsheet should look like. Now this is one place where it's going to be very useful for you to know how to use formulas, because even though there's lots of entries there, a lot of them are calculations. Okay? Now, when we hook up the oscilloscope, let's couple that one here, when you see a shortcut right here for the oscilloscope. You click on it and hopefully it will come up. If it doesn't, that means it's probably because the computer has been wiped and re-imaged, and it needs to add the USB driver for that again. That takes a while. It takes a good couple minutes. And if that's happening, what you will do is you'll look down here on the USB thing that says safely remove, where usually you would eject a flash drive if you wanted to keep it safe. And you'll see it's got this little spinny icon thing going around, and you got to wait till it's done. It's a real pain, and I'll try to remind Greg, and hopefully he'll check them all out to make sure they all work beforehand. So we got it hooked up to the USB. That's all you need. This is the Larger Pro cable. We don't care about it. And I've got 3 of these probes hooked up. Now what I usually do is I like to have, you see here it says output, input A, or channel A, and input B, or channel B. I usually like to have the gray one on the output as the signal generator, and the 2 black ones being the input. So what we're going to do is we're going to start off without this at all. We're just going to use channel A. That's this cable right here. And we have here the waveform generator, which we're not going to use yet, the scope, which is right there, and this here, this digital I/O, because this actually does other stuff too. It's actually a logic analyzer too, but we're not going to use that at all, so we're just going to close that. You can close that, it doesn't matter. Okay, you can also make this bigger, like that, which is really cool. That way, my cameraman doesn't have to zoom in on everything so much. Now, if we wanted to know what the amplitude of this was, we're going to be concerned mostly with the vertical settings. Now, we have a red and a blue signal. The red is on channel A, and the blue is on channel B. So how do we do that? Well, all we have to do is hold it, and we can do this with one hand. All right? We put the black on the bottom part here, and we put the red on the top. And as you can see, it jumped up. How far? Well, it looks like about 1.5 divisions. A division is a box. There's 10 boxes going across and 10 boxes going up and down. So 1 box is a division. And right now we're set at 1 volt per division. If you look at it, so that would mean that this is 1.5 volts. Now let's do a little bit of a sanity check and read the side here. What does it say? Can you see what it says?
Can't focus it.
You can't focus it. Well, can you read it? What does it say?
1.5 volts.
1.5 volts. In other words, it actually worked. If we wanted to get a more accurate reading, maybe the battery's a little low, we could do is we could put this thing back here like that. I don't have a good connection. It's hard to do this with one hand while I'm talking. And instead of setting it to 1 volt per division, we could do this plus thing, which makes it bigger. And now we're at 500 millivolts, or half a volt per division. And you see, that's half a volt, 1 volt, 1.5 volts. Isn't it amazing? It actually works. Now, if we went to another one, up to another, say, increase it again, it went away. Why? Well, because it's above the top of the signal. When I'm making a good connection. Above the top of the scope. So we've saturated it. It's too high. So, if you want to look at it this way, if we bring it down something like to 5 volts per division, that one's too low. And if we go up to 0.2 volts per division, that one's too high. But just like Goldilocks, either say half a volt per division, that one is just right. So like I say, you want to be like Goldilocks here. Not too high, not too low, just right. Where's that going to depend? Is it always going to be half a volt? It depends on your signal. So you measure that one, and this is pretty easy now how to do this. We've seen how to do this. What we're going to do is we're going to fill it out, scale per division. In this case, we did 0.5 volts per division. We had 3 divisions. So the peak-to-peak voltage, and if you read my little thing here, Matt says this is the number of vertical divisions times the scale setting. That X means times, by the way. And so 0.5 times 3, that's 1.5. Hey, that's pretty easy. All right, you got to fill that one in yourself. Now we're going to make things just a little bit more complicated. I know you wanted to. Now, get rid of the battery. All right. Don't do that. Craig would be mad at you if you did that. And we're going to take the gray cable, in my case, the output signal, and channel A cable. We're going to hook up black to black and red to red, because we're color coordinated. All right. And what we want to do now is use both the signal generator and the oscilloscope together. So you set the signal generator frequency to 1200 hertz. How do we do that? Well, if we go to the waveform generator, we can just click on, don't do that, that's the maximum frequency. Because you can slide this thing up and down. All right. In fact, let's show you how. I'll give you a signal. You can slide the frequency up and down, and it'll go anywhere between 0 and 200,000 or something like that. Ridiculous. So how do you get it exactly on 1200? Well, there's an easy way to do it. You just click on this number here and you type in 1200. Okay, so you click there, you type 1200. Now, the nice thing about this, which is unlike the battery, see, what if the battery, if that came out negative, what would that have meant? Do you know? What if the battery came out at negative 1.5 volt? Does that mean that it was made wrong? No, it meant that you switched the 2 leads. On this one here, it doesn't matter because it's going back and forth on both sides. Okay. So, we have a signal. It's at 1200 hertz. Now it asks for the scale setting in volts per division. Now, I did set the amplitude here too. This is how you change the amplitude. Oops, I still have that up. You can change the amplitude of the signal. That's the signal generator part of this. It's not changing the scope. This is sort of like a microscope. This is what we're trying to measure, but we can control it. So the microscope has got controls, so we can go horizontal, change its magnification. All right. So just set it at 50, and you can just type it in there, just like this one here. Just set it at 50. That'll be fine. Okay. Now, when we want to measure this, it has a nice little feature here that we can bump it up and down, sort of like moving your slide on your microscope. So it just touches either, say, at the bottom or the top, and you can even type it in here. So let's say this, let's put it at negative 0.067, and it still doesn't touch it where I want it to. Let's try it at a negative 0.06. This is just to make your life easier. I'm not doing a very good job of it, so I'll just give up for now on that. I'll try to do it this way. There. Okay. So now I've got it right along the top here. It could be either the top or the bottom, just to make your life easier. We are going to measure the amplitude. Well, we do it the same way we did it with the battery, except we're going from the peak to the valley. So we count, we say, all right, scale settings, volts per division, it's still 0.5. And we say the number of vertical divisions. And you say 1, 2, 3, 4, 5, and then say 5.8. Okay? So 5.8 it is. That's pretty easy. You multiply 0.5 times 5.8 to get the peak-to-peak voltage, and you get 2.9 volts. At least I did. You might. Your results may vary. So may your mileage. Now we've measured things again horizontally. vertically. But you may have noticed that this part of the lab, we have something a little bit additionally interesting, it's not straight flat across. The signal actually goes up and down like a sine wave. So we might be interested in the peak, the frequency. So we got to figure out how to do that. So we put in, and this is probably a good setting right now. Again, you can mess with it by changing this one here. Now this changes it for both channel A and channel B. They have to go together. The volts per division vertically do not, but the time signal does. And we can say, all right, well, if we change it like this, we can get more of them in there, and you can get so it's a blur, and you can get so it's just part of it, and that's not enough. So we want it right about there. That's good. Okay, and you might remember this from 20L if you took 20L. So here we say the scale setting per division, and it says 1 millisecond. What's 1 millisecond? Well, we want it in time. We want it in seconds division, so we'll say 0.001. That's a millisecond. Okay. Now, what we're going to want to do is we're going to want to take the signal at one point to another point. Let's say we'll go from right here to right there. All right, and we're going to count those divisions. So here it's just, let's say it's that. Look at this. Say it's at 0.1, but let's say 1, 2, 3, 4, 5, 6, 7, 8, and then about point. What do you think? 0.3? She says 0.4. But then we started off here at 0.1, so it's going to be from 0.1 to 8.4, so we'll say 8.3. All right, 8.3 divisions. All right, now the total time then is going to be this times this, and the little comment there says that too, so you don't have to remember it, trust me. See, Matt says that's so that you can hear what I'm saying when I'm not even there. So that's going to be 0.0083 seconds. Now if we look back on that, how many periods was that? Did you count them? I didn't. We start from here and we go 1, 2. Oh, don't do that. This is not 1. This is 1 because it goes from here back up to here. That's 1. Then that's 2. That's 3, 4, 5, 6, 7, 8, 9, 10. 10 periods. So we'll put that in there. So how long is one period? Well, if you read the little tip on there, it'll tell you, or you can just believe me. That's going to be the total time divided by the number of periods. So it's going to be 0.00083. Now the frequency, that's going to be 1 over the period. Equals 1 over, I'll use a formula for this one because I'm lazy. And it came out to 1204. Well, what did we have it set at? We had it set at 1200. So what's our percent error? Well, there's a formula right over here on how to figure out your percent error. You can do it. I'm not going to right now. All right, so you do it for 3 different frequencies, 1200, 7400, and 12400. You should get pretty accurate results. In my case, I'm down less than 1%. You guys can probably manage to do that too. Okay, so for our next step, it also asks you a question. How can you reduce the measurement uncertainty? Think about it. If you need help, I'll tell you. For our next part, and this is where it gets hard, or long, we're going to test something called a low-pass filter. Now, I've already set it up on here, and there'll be a setup that you can duplicate. So what I would do is I would bring your board up to the front, to my setup, and duplicate it here. All it is a resistor and a capacitor. The resistor value is 100 ohms. All right. The capacitance, as it turns out, is 220 nanofarad. That's 220 e to the negative 9. All right. Now, that gives you a cutoff frequency, and you can figure out that cutoff frequency with the formula I gave you. It's equal to 1 over 2 times pi times the resistance times the capacitance. So let's put that in here and see what we get. Actually, I know, but we'll try it anyway. Equals 1 over 2 times pi. Remember, the formula for pi is the pi with open and closed parentheses times the resistance. Resistance is futile. whoops, times the capacitance. And we did not get the right answer because I didn't make the formula right. These should all be in parentheses. So now it looks like I'm getting about 7,230 hertz for my frequency. But it doesn't hertz that much. So I said round it. So round it to the nearest 10 hertz. Round it to the nearest 100 hertz actually. So let's do it 7,200 hertz. Okay? So now what we're going to do is we're going to start off, and I'll have this list of frequencies here that might change. 720 times 7,200 times 0.1, that's 720. Okay? And we're going to want to generate that from the signal generator. And we'll keep, so we go over to the signal generator, and we type in 720. The actual frequency isn't that big of a deal. If you're at 700, I don't care. The point is you just need the data points. All right? And now we're going to hook up the low-pass filter into our system. First, we have to hook up the input signal. This will also be up at the front. You have red to red here. Make sure you hook it up to this one here with the cable, not the one that's not hooked up. If you get no signal, it's because you hooked it up to the wrong cable, probably. Yes, my hands shake too much. All right, like that. Now the signal is going into the low-pass filter. Don't worry too much about what a low-pass filter is. That's not really the point here. The point is to let you learn how the oscilloscope works. Now we have channel A, and we're going to hook up channel A so that we can see what the input to this is. And the way to do that is to hook it up across from all the way from the end of the capacitor. So it's hooked up essentially to this black one here. You got to make sure that you don't pull out the lead from your capacitor and all the way to the resistor. And this is actually hooked up straight the same as these ones here. Okay? So we should see about a 720 hertz signal. Trust me, we probably do. Now we want to see what we get from an output. Now the output is going to be across the capacitor. That's the way these filters work. So we put one of these leads here, the red one on that side, and the black one to the black one here. It's all ground. So we got ground, ground, everything's a ground, ground. All right, and you may see that the signals look different. But they shouldn't look different, because it's below the cutoff. Why do they look different? Well, they actually aren't different, because here the channel B is set to 1 volt per division and channel A is set to half a volt per division. If we put them on the same scale, they look identical. Now what I want you to do at this point, when you set it all up, is run the frequency up and down. And what you should see is that as you start off, they may vary some, but they're going to stay right together. And then as you get up above 7,000 or so, the cutoff frequency, you're going to see that the blue signal as a percentage of the red signal should be going down, 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 until it's gone. Okay? Now, what you're going to do here is we're going to start, like I said, at 720, not 1.3. And we're going to make the measurements on both the blue and the red signals for, well, we'll start with the blue, the red signal, sorry. The scale percentage right now is 0.5, 500 millivolts per division. The number of vertical divisions, so we can mess around with that, and we'll get, see, 1, 2, 3, 4, 5.8. Just make a good estimate. The peak-to-peak voltage then will still be 2.9. which is not the same as 3.9. Then we'll do the same thing for channel B, and as you can see, it's going to be the same. The scale setting is still 0.5. The number of vertical divisions is still 5.8. The peak-to-peak voltage will still be 2.9. All these are in fact, if you want, you can make these into formulas to do the math for this column and this column, and more of them that you're going to see here. Now we're going to take the normalized peak-to-peak voltage. So everything else we've been doing before has been abnormal. How do you get that? Well, if you read the little tooltip there, it says divide all the peak-to-peak voltage in the previous column, that's column I, by the input amplitude. So you divide channel B by channel A. All right, and if we do that, we're going to get 1, as we know, but let's just make it a formula to make our life easier. Done, 1. Oh, that was easy. Now we have to get the response. And I'm going to make this a little bigger so I can read it. Yes, there's lots of columns to fill out. The response is just 20 times log 10 of the normalized signal. So we can make that a formula too. I think my cameraman's getting tired. Are you? Yes, she is. But that's what you get for borrowing my car. You have to be my cameraman. Okay. And it came out to 0. Oh, is that a problem? No. Log of 1 is 0. All right. Now, most of the numbers after that are going to be either very small or they're going to be negative, and they're going to get more and more negative as we go along. Now, on channel B only, we're going to get the scale setting time per division, and it's just like what you did in the first one. So we would take a look at this. We'd say the time per division now is 1 millisecond. It still is. So it's 0.001. Horizontal divisions, well, I'm not going to go through all the math here on this one here, but you would start from somewhere right here and go to here, and that's 1, 2, 3, 4, 5, 6.8. 6.8. The total time on that's going to be 0.0068. The number of periods on that, and this is going to get very repetitive, I know. It's 1, I'm just doing it backwards because we'll start from here. 1, 2, 3, 4, 5. 5. So this is going to be, the period time is going to be the total time divided by the number of periods. And then the frequency is going to be 1 over that. We're almost done, the whole lab. This is easy, right? And I got 735, which isn't too bad considering how fast I'm doing this. And you figure out the percent error, same way. Okay. Then you do it again for more frequencies. I'm going to skip ahead to a much higher frequency. Let's go up to, let's set our frequency up to, let's go all the way up to 14,000 or so. I don't know if that's going to be one of the ones that you'll have. Now, as you can see here, it's a lot smaller. You can make this, the red signal, bigger and adjust it. Doesn't really matter. So let's get it right up to the red, that line right there. And that's good. If we had to, we could adjust the offset. You can't always do that, but this time we can. And then we're going to have to change our sampling time to about, wrong way, I always go the wrong way. Well, that'll be good enough for now. Okay, now one thing you notice is they're not right, not only are they, the size is different, but they're out of phase too. That's going to become important for the next lab, but we're not going to deal with that today, okay? Just see that, yeah, they're not in phase anymore, right? It's important to be in phase. Not really, just important to know. So here we do the same thing. Now in the red one we got 3.7. I'll just make it 14. I'm just going to write in 14,000 here. Okay. So we have still at 0.5. How many did I say it was? 3.7? 3.7. You figure it out. That's going to be 0.74. No, I'm sorry. That's going to be 1.85 volts. The scale setting for the other one, we can figure that out, make all the measurements, blah, 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 go all the way down. But you can see what's going to happen. Let's do this, at least the first couple. So here we only have, let's see, it starts out here, 1 point. Let's blow this one up a little bit just so we can see it better. They don't have to be on the same scale, vertically. Now if we do this, we say, all right, we're at 0.1 volts per division. And we have, let's see now, 1, 2, 3, 4, 5, 6, 7, about 7.4 here and a little bit, say 0.1 there, so 7.5. All right, our peak-to-peak voltage now is going to be 0.75. Our normalized peak-to-peak is going to be equal to, just copy the formula down, 0.4. And our response now, it's going to be a negative number of negative 0.78. Okay? So then what I want you to do is take data for all the points that you see on here, and then you're going to plot the signal generator frequency versus, on the x-axis, versus the response on the y-axis. Okay? So that's going to take you a little while, but it'll give you lots of practice with the oscilloscope. Remember, like even on this one here, if you look at this, well, you might say, well, couldn't we have changed the vertical setting for the red signal? And yeah, we could have. It would have made it a more accurate answer. Why didn't I? Well, because I didn't want to bother. No, because I'm trying. You don't want to get too high, but that would work good right there. Now this one's at 0.2 and this one's at 0.1 volts per division. Okay. So you take a whole bunch of data points, and then you're done, right? No, there's one more thing you got to do, but I don't want you to even watch the next video until you get done with this much of the lab. So right now, we're going to stop this video.